Hi everyone, welcome to part 1 on our video lecture on section 9.1 and 9.3 dealing with differential equations and their applications. In this video, we will be resuming where we left off in class and continue our practice with the method of separation of variables, which again was one of the methods that we can use to solve differential equations. Now this particular approach to solve differential equations only worked whenever we could write an x with the dx and the y with the dy on the same side of the equation so that we can integrate them, as we have here. Now, if you cannot put the x with the dx and the y with the dy, you cannot use the method of separation of variables, and there's other techniques that we can use. However, these other techniques, I'm going to reserve them for another class, which is Math 253, dealing with the intro to differential equations. Alright, so in class we solved the problem dy dx equals to x over y, and this one here we were able to solve with the method of separation of variables. And I want to remind you that whenever we're solving a differential equation, we will need to include our constant of integration, which meant that we are going to be getting a general solution. Now later on in this video, we're going to be taking a look at a problem where we are given an initial condition, so we are able to find the particular solution. So without further ado, let's go ahead and continue with another problem, given here by dy dx equals to y over x. Alrighty, so the first thing to do here is to get the y's with the dy's and the x's with the dx's. So for this problem here, I'm simply going to go ahead and interchange the y and the dx in the equation. So it's going to give me here a dy over y equals to a dx over x. Alright, so now that we have the y's with the dy's and the x's with the dx's, we can go ahead and integrate both sides. And we're now going to be getting, put here, an ln of y and ln of y equals to an ln of x. Now once we do the integration, we do add our constant of integration here, and we are not done because we're not looking for the ln of y, but we want to get the y by itself. So at this point you might remember that to get rid of the natural logarithm, well, we need to exponentiate everything here. So we're going to get an e to the ln of y equals to an e to the ln of x plus c. Now it is at this point that I do want to mention a special trick that we're going to be using through the rest of this lecture. And it's not really a special trick, but it is just more of an application of the rules of exponents. So recall that whenever we have a raised to the m times an a raised to the n, since we're multiplying two factors with the same base, different exponents, well, you guys remember that all that we need to do to simplify this one here is to add the exponents. However, notice that this one here is an equation, it's an equality, so it means that the right hand side is the same thing as the left hand side. So what I'm going to be doing here is I'm essentially going to look at the right hand side here, which says that, hey, whenever you have a number raised to a sum of powers, you can actually split it up as a product. So going back to our example here where we have e to the ln of x plus c, I'm going to go ahead and rewrite this one as e to the ln of x times e to the c. Now at this one here, since, I don't know, we might use more operations with the constants, I'm going to go ahead and label this constant of integration as C1. Alright, C1. Okay, now, here's a question. If we have e raised to a constant, well, isn't this still a constant? So this is still some other constant. So we're going to have here the e to the ln of y is equals to c times the e to the ln of x. Okay, now at this point, we're going to be going to cancel the exponentials and the logs. So we're going to get a y is equals to a c times x. And there we go. Here we have our general solution. Now throughout this lecture, guys, I'm going to be using this trick quite frequently, so I'm not going to be showing the steps anymore. I'm just going to go ahead and use this one. Okay, now let's go ahead and take a look at another problem so we can start to get more comfortable. Alright, so this third problem is giving us the equation y prime is equals to 2y times t. And again, we see some derivative, so it is a differential equation. So let's go ahead and solve this one here through the method of separation of variables. Okay, so the first thing that I noticed for this problem compared to the other ones is that we have the prime notation. I don't really see a dy dx. Although technically this problem, since the other variable is t, we do want a dy dt. So the first thing to do for this one is to rewrite it so that you have a dy dt. So we're going to have here dy dt is equals to a 2y times t. Alright, so now the next step is now to actually separate the variables. So we want the y's with the dy's and the t's with the dt's. So this one here is going to give us a dy over y equals to a 2t dt. Okay, there we go. Now we can go ahead and integrate both sides. And this is going to give us an ln of y on the left-hand side. And the integral of 2t is going to give us a t squared plus c. Okay, now we're pretty close to being done. Now we need to get the y by itself, so we go ahead and exponentiate both sides. And this is going to give us here a y is equals to e to the t squared plus c, which, using the trick discussed in the previous problem, this one here could be rewritten as c times e to the t squared. Now to differentiate the c that we had here as the exponent and the one that we have here as the coefficient in front of the exponential, we're going to go ahead and call the c here that we added our first constant of integration as c1. So c1. So there we go. Now this c, that's the constant or the coefficient of the exponential. There we go. It's just the plain old c. Alrighty. So our solution for this one then is y equals to c times e to the t squared. And that's it. Not too bad. Okay, now let's take a look at another problem here, but this one here is going to be slightly different because notice for this one, we're given the differential equation x times y plus y prime is equals to 100x, but we're also being told that y of 0 is equals to 90. Now you may remember this type of problems back from calculus 1, where we had here the y naught equals to 90 was our initial condition. But you might also have seen it as the initial value. Alrighty, so let's go ahead and solve this problem. So we have x times y plus y prime is equals to 100x. Alright, so again, remember the first thing to do here is to rewrite it in terms of dy dx. So we're going to have x times y plus dy dx is equals to 100x. Alright, so let's see if we can go ahead and get the x's with the dx's and the y's with the dy's. Alright, so the first thing to note is that, well, I can go ahead and subtract an xy from both sides, which would give us then dy dx is equals to 100x minus xy. Alright, so why am I choosing to do it this way? Well, this one here is a little bit trickier because notice that in the other problems, we typically were dealing with just multiplications of x's or y's or x's or y's and dt's, things like that. But this is the first problem that we are encountering a sum. So how can we handle it? Well, the reason that I moved the x's with the x's is so that I'm able to factor out an x from both terms here. So this is going to give us then a dy dx equals to an x times 100 minus y. Okay, now I have a single x, and now we can go ahead and put the x's with the x's and the y's with the dy's. Alright, so rewriting this one here, I'm going to get a dy over 100 minus y, and that's equals to an x times dx here. Now we have the desired form, and we can go ahead and integrate this one. Okay, so integrating the right-hand side, I will be getting an x squared over 2 plus c. Let's call this one here c1. But what about our left-hand side? Well, this one here, we can go ahead and use a u substitution. So I'll let u equals to 100 minus y. So my du is going to be a negative dy. Okay, so rewriting this one, and maybe I should have saved this one for the right-hand side here. All right, so what are we going to be getting? Well, let's see. All right, so continuing with our integral here, the dy over 100 minus y, this one is going to be the same thing as a negative du over u, which is a negative ln of u, absolute value. All right, so putting everything together, we're going to have a negative ln of the absolute value of our u, which was 100 minus y. Okay, now let's see if we can get the y by itself. At this point, since I do have a negative, I'm going to go ahead and multiply everything by a negative. So I'm going to have an ln of the absolute value of 100 minus y is equals to a negative x squared over 2 minus a c1. But at this point here, guys, since it's still a constant, this negative c1, I'm just going to call this one here a positive c2. Okay, now continuing the process, we want to get the y by itself, so we can go ahead and exponentiate both sides, which will give us 100 minus y is equals to and e to the negative x squared over 2 times, now again guys, using the same trick as before, we can go ahead and separate the sum in the exponents as a product. So c times, well, just c basically. And I'll say here as a reminder that this c was equals to e to the c2. Okay, now we are very close to being done. We just need to get the y by itself. So I'll simply add the y here and subtract everything here, which will give us a y is equals to 100 minus e to the negative x squared over 2 times the c, which I guess I can rearrange here. Okay, now again, this is the general solution, but this problem in particular, though, was asking us for a particular solution because we're trying to figure out what is going to be the equation that also satisfies the condition where y of 0 is equals to 90. So for the initial value, I'm going to go ahead and plug in 0 for our x's, and we know that we should be getting a 90, so we're going to have here 100 minus c times e to the 0. This one here should be equals to 90. So since e to the 0 is 1, we're going to get then 100 minus c is equals to 90. And solving for c here, we get to see that c is equals to a 10. Alrighty, so then our particular solution here, let me move this one further up. So the particular solution is going to be given by y is equals to 100 minus 10 times e to the negative x squared over 2. And there we go. We'd be done with the problem. Now this one here again was a little bit more challenging because, well, we needed to factor out an x so that we were able to use the method of separation of variables. Okay, so this is the last example that we're going to be doing. Well, last example without any context, because now we're going to be taking a look at some applications of the differential equations, so that we're going to be taking a look at word problem. Alright, so let's take a look at our first type of application problems, which deal with continuous growth and decay. Now, in many applications, the rate of change for a quantity y is proportional to the value of y. Now, what this is telling us here is that the rate of change, dy dt, is proportional, so we know that we need to include a k value. It's proportional to the value for y. So we can see it here, dy dt is equals to k times y. Now, since the type of applications that we're going to be encountering with a lot of the times deal with population, I'll rewrite this differential equation as dp dt is equals to k times p, where p of 0, the initial value, is given here by p naught. And I'll put this one here as the initial condition or the initial value. Okay, so let's say that we know the differential equation. How can we find the p-value? Because we don't want dp dt, but we want the function p. Alright, so this problem here, as you can tell, is a problem involving the method of separation of variables. So I'm going to go ahead and use the method of separation of variables to solve this equation, this differential equation, and we're going to get here dp dt is equals to k times p, where we can go ahead and get the p's with the dp's. So we're going to get dp over p is equals to k times dt. Integrating both sides, we're going to get here an ln of p is equals to k times t plus c. Now, exponentiating both sides, we're going to get here a p is equals to e to the kt times, I'll call this one here c1, and using the trick that we did in the first couple of examples, just put this one here as c, and there we go. We come up with our equation for p. Now, to be more precise here, if we know that p of 0 is equals to p naught, well, putting it here as p of 0 is equals to e to the 0 times c, and we know that this one is equals to p naught, well, you get to see here that since e to the 0 is 1, our c value is p naught, so the equation that we're going to be working with is p of t is equals to p naught times e to the kt. Alright, so now just let me rearrange this. Okay, there we go. So notice, in class, I mentioned that technically you guys have been working with differential equations in the past, although you may not have known this. So notice that this equation is simply the natural exponential function, which you have encountered in previous algebra courses. Now you know where it's coming from. It's actually coming from this differential equation where the rate of change is proportional to the value of the function at a particular time. So I'll put here, and there we go. Alrighty, so let's go ahead and take a look at a word problem here. This problem, example 4, is asking us, well, it's just telling us that the rate at which a population is growing is directly proportional to the population. Alright, so what I just read right now is, okay, well, they're telling us here that dp dt is directly proportional to the population. So we're seeing here that, okay, well, it looks like we're dealing with this type of differential equation, which we know will result in the natural exponential function. Now, what else is this problem telling us? Well, they're telling us here that the population was 100,000 people at the end of 1990, and it was 120,000 at the end of 2010. So with this information, we want to go ahead and write down a function, p of t, to represent the population at time t, where t0 corresponds to the end of 1990. And with this function, we want to figure out what will be the expected population by the end of the year 2015. Okay, so how do we begin this problem? And again, we begin by rereading the problem and noticing that, hey, it looks like we're dealing with a typical differential equation that's dealing with continuous growth, because it was telling us that the rate of change was proportional to the population. So, since we know that we're dealing with the differential equation, dp dt is equals to some constant of proportionality k times the population p, we know that this type of problem will result in the solution of the form p of t is equals to some p naught times e to the kt. Now, you don't need to solve this differential equation all the time, guys. I'm only solving it once, so you know what to expect for the solution. So I don't expect you guys to solve this problem again just to get this form. You can just use the results that we're getting from the formulas. So now that means here that at this point, this just became a typical pre-calculus problem. So let's go ahead and solve this one then. Alright, so we want to go ahead and write down the function that is representing the population at a time t, where t is 0, or t equals 0 corresponds to the end of 1990. Alrighty, so this problem is telling us that at the year 1990, so I'll put here for part A, at t equals to 0, we know that p of 0 is equals to 100,000. So we have part of our equation right now. We already know that this one is representing the p naught. And we also know that in the year, let's see, 2010, the population was 120,000. So I'll just highlight this one here. 1990 was t equal to 0, and 2010, well, 2010 is 20 years after 1990. So 2010 is equals to t equals to 20, or it corresponds to that t value. And that's what I'm going to use right now. At t equals to 20, aka the year 2010, p of 20 is going to be equals to, now we know that the equation is going to follow the form p naught times e to the kt, but we already happen to know p naught is 100,000, so this one here is going to be equals to 100,000 times e to the kt, so e to the k, I'll put the k here in green, times the time, which was 20, and this one here is equals to 120,000. And again, no calculus. This is just a pre-calculus problem or a college algebra course problem. So isolating the k, I'm going to go ahead and divide by the 100,000 on both sides. And that's just going to leave us with an e to the 20k is equals to 1.2. I guess I'll divide here by the 100,000. Okay, alrighty, so now we're dealing with a simple exponential function, e to the 20k is equals to 1.2, so we can go ahead and take the ln of both sides, and that is going to give us here, I'll put the ln in orange, the ln of e to the 20k is equals to the ln of 1.2, which the e's and the ln's cancel out, leaving us a 20k is equals to the ln of 1.2 divided by 20 divided by 20 gives us the k value is equals to the ln of 1.2 over 20. Now putting this one here into my calculator is giving me approximately, well, you know what guys, I'm going to leave the k value like this because I don't want to be dealing with decimals that I need to carry over. So I'm just going to leave my k value like this, and I'm going to put this in color green. So this is our k value. So that means that our equation, p of t, is the following. We're going to have a p of t is equals to 100,000 times e to the kt, where we know that the k is the ln of 1.2 divided by 20. Alrighty, so with this equation, and I'll put here again, where k is equals to the ln of 1.2 over 20. Now I guess I could have put it into the equation, but I don't want my equation to look more complicated than it really is. Alright, so for part B, we want to see what will be the expected population at the end of 2015, but 2015 here corresponds to the t-value of 25. So for part B, all that we're looking for is, hey, what is the function evaluated at 25? So this is going to give us then 100,000 times e to the ln of 1.2 divided by 20, and you're multiplying that exponent by 25. So it's going to give us here, I'm going to go ahead and plug in everything into my calculator, and I got approximately 125,596.21. Okay, so just put here people. There we go. Alright, so I just noticed that I used a lot of colors here, but at its core, guys, this problem, you just need to recognize which type of differential equation that you're working with, and we set up the problem, we know what the solution looks like, and then just use that form of the solution to figure out the rest. And it seems more like an algebra problem. Alrighty, now I want to take a look at one more example, or I'll continue with this next example in the next video. So I'll see you guys in part 2.